all needy people.
There you go. Not you, Emily. That was just really bad time. But kind of funny, actually. Oh, man. Alright, so in your class starter, you've got two related rates problems that we're going to work through. And then today we're going to start our discussion of optimization, which is really just an application of the extreme value theorem, which you already know. So in our notes, we'll kind of review through that and then talk about optimization and work through some examples of that together. Okay, so it says, a 6-foot tall man walks away from a 20-foot lamppost at a rate of 30 feet per second. How fast is his shadow lengthening? So probably the first thing we need to do here is draw a picture, yes? So what should our picture look like? Yeah, so we have a lamppost, correct? So this is the lamppost. And then somewhere over here we have a man. Agreed? Okay. So the man is walking away from the lamppost, right? And so we know that this distance is changing, yes, because he's moving further and further and further away from the lamppost. So if this is changing, we need to give it a variable. What variable you want to use? X, all right? And then in addition to that value changing, the man's shadow is over here. And it is growing as he walks further and further and further away from the lamppost. So since this distance is changing, or this length is changing, it needs a variable. So what do you want to call it? All right. So we know that the light's shining on down, and we can create that's a really ugly triangle, but we can create a triangle like such. Yes? Okay. So we have some constants here. What's not changing? Yeah, how tall is the lamppost? 20 feet. And what else isn't changing? And if it is changing, it's not changing so fast that it's going to affect our problem. The height of the man, right? How tall is our man? 6 feet. Okay. So in addition to those things, the 20 feet, the 6 feet, and then this distance, which we know is changing, and the length of his shadow, which we know is changing, what else were we told in the problem? The rate he moves away from the lamppost, yes? So what changes at that rate? Which of our variables? X, good. So that's dx dt is 3 feet per second. And what do we want to know? dy dt. Okay. So we have some triangles here, yes? And when you have one triangle inside of another triangle, what do you know about those triangles? They're similar figures, right? So our equation is actually going to be a what? A proportion, right? So do you want to do little triangle first or big triangle first? Okay, so in the big triangle, we have a height and we have a base, correct? Which one did you use on the top? Okay, so the base of the big triangle is x plus y, and the height of the big triangle is 20, right? And that's going to be equal to the base of the little triangle over the height of the little triangle, which would be what? Y over 6. Go ahead, can I plug anything in right now? No, because what have we not done yet? Differentiate. Would we like to do a little bit of algebra before we differentiate? Yeah, what would you like to do? Cross multiply, which is going to give you what? 6x. And you can differentiate at this point if you want to, or do you have some like terms that you might be able to combine? Yeah, so you probably moved the 6y over here if I had to guess. So that gave you 6x equals 14y. Now is this pretty easy to differentiate? What's the derivative of 6x with respect to time? 6 dx dt, and what's the derivative of 14y with respect to time? Good, so now we can plug in what we know, which is dx dt, right? What's dx dt? 3, so 6 times 3 equals 14 dy dt. And when you simplify that, you got that dy dt is what? 9/7 what? Feet per second. Very good. I agree. The cones, yeah.
I like it.
First, I
The cones,
I didn't get them now.
now they make sense.
I like it when there's a formula that's complicated, like volume, surface area.
Then you don't have to think so hard because you know what the
You
formula
don't
is
have
going
to
to be.
pick it up.
Yeah. I agree. I agree. All right, let's look at number 2. I know. I missed lots of spots. That's depressing.
Yeah, I know. I was like, why would I sit there and wait till like 8 and it was still dark?
I think I'm supposed to sleep in.
Because I have slept in
When you wake up at 5 and you're like, probably have another hour.
But it's also when you wake up at like midnight and you think it's like 5 a.m. and it's only midnight. I just want like 6 hours to sleep.
It was the best day ever.
Sometimes I like leave set an alarm so I can like turn it off.
I'm not kidding.
On weekends I like leave my 6 one so I can just be like,
Nope. Not me. Yeah, I can't turn it off. I'll be able to.
Well, I just fell asleep like on my last night. Didn't set my alarm.
Nice.
So,
Is there a way you can change like this snooze period? It's like
Yeah,
yeah.
Yeah, mine like
it's under like settings.
that's so
Do you want to make it bigger or smaller?
I'm always awake. That's
Make it like
I hate how long it is.
We're like
9 minutes is too long.
I just so much.
And it's so random. Why 9 minutes? I don't understand.
that makes you so
All right. And number 2, it says there's a camera mounted at a point 3,000 feet from the base of a rocket launching pad. If the rocket is rising vertically at a rate of 880 feet per second, how fast must the camera's angle of elevation change when the rocket is 4,000 feet above the launching pad to keep the camera aimed at the rocket? So we need to draw a picture, yes? What do we start with? What's in the first sentence?
We have the camera.
We have a camera, so here's your camera.
It's 3,000 feet from something.
It's 3,000 feet from something. So this would be the launching pad, yes? Is the camera going to move further away from the launching pad? No, right? So that 3,000 is going to remain constant in our problem. So we can put it on our picture because it's not going to change. Okay? What's going to happen from the launching pad? Yeah, the rocket's going to shoot up, right? So here goes your rocket. He's moving, right? So do we want to put a value on the side with the rocket? No, because it's changing. Agreed? Okay. And our problem is asking about what? The angle of elevation. So that would be the angle from the camera up to the rocket. Yes? Okay. So let's go ahead and give these other 2 sides variables just so that we have them. What do you want to call this? Y, okay, and what do you want to call this? Okay. I don't know why, but okay. So Megan. All right, so let's list what we know besides the 3,000 because that's a constant. We've already put it on our picture. Tell me what we know. dy dt is what? 880, because that's how fast the rocket is moving vertically, right? So that would be his rate of change. What else do we know? Yeah, we want the theta dt at the instant that y is 4,000 feet. But we know that, we hope the rocket doesn't just get to 4,000 feet and stop, right? So we know that this is changing, so we're going to not use it until we're ready to do so. Okay? All right, so we're looking for d theta dt. So when we go to write our equation, we need to make sure that there's a theta in our equation, which means it's going to have to involve what? Trig. Luckily, it's a right triangle. That should make it pretty easy, yeah? Okay? So what we want to do is we want to make sure that whatever right triangle ratio we use, it involves the sides we actually know things about, yes? So what sides do we actually know things about? We know the 3,000 is not going to change. That's our constant. And then the y, we know dy dt, and we know our instant of y. So that's the opposite and the adjacent. So we're going to use what? Tangent. So we're going to say the tangent of theta is always equal to what? Y over 3,000.
How do you know it's true?
Because you want to use this because it's a constant. Otherwise, you'll have two variables and you have to use the quotient rule. That's this, right? And then we choose this one because we know things about it. Okay? So it's whatever side you actually know things about, those are the ones you're going to want to use. Okay? All right, before we can plug anything in, what do we have to do? Take the derivative. What's the derivative of tangent, bless you, of theta with respect to time? Secant squared theta d theta dt. Good. Okay. You do not have to use the quotient rule to find the derivative of y over 3,000. I would highly suggest that you don't, because when y'all try to use the quotient rule to find the derivative of that, you do it wrong, because you forget that the derivative of 3,000 is 0. Okay? So, y over 3,000, for those of you, I'll write it on here so you can see it too, is the same thing as 1/3,000th y. It's just a linear function. Okay? So what's the derivative of y over 3,000? 1 over 3,000 dy dt. Okay? So you can do it. Okay? So now let's plug in what we know, and then we'll figure out what we still need to know to solve for d theta dt. So tell me what we know. Dy dt is 880. So we know this side is really 880 over 3,000, or if you want to reduce that, then you can do so. Okay. 22 over 75. That's a lot prettier than 880 over 3,000. So I'm going to go with that. On this other side, we're trying to solve for d theta dt. So what's in the way? The secant squared of theta, yes? Okay, so we want to get rid of that. Agreed? Dividing by secant is the same thing as doing what? Multiplying by cosine, right? Because they're reciprocals of each other. So rather than dividing by secant squared, to get rid of this secant squared, I'm going to multiply by cosine squared of theta on both sides. Okay? Whole lot easier that way. So in order to be able to solve for d theta dt, all we need to know is the cosine of our angle at the instant that they gave us, yes? Okay? You do not actually have to find the value of the angle, because it's not just theta, it's cosine of theta, right? So we want to replace this entire thing with the value of cosine, okay? So in a right triangle, how do you get cosine? Adjacent, which is always 3,000, right? Over the hypotenuse, which we called it, okay? But when you're dealing with the derivative, you're dealing with the derivative at this specific instant, yes? When y is 4,000, okay? So can I figure out if this side is 3,000 and in my instant y is 4,000, what n has to be at my instant? Yeah, you shouldn't even really need to work that out, because if one's 3,000, the other one's 4,000, what's this one got to be? 5,000, right? Because it's 3, 4, 5, just add some zeros on the end. So at my instant, the cosine of theta is 3,000 over 5,000, which is really just what? 3 over 5, okay? So this is always true. This is true at my specific instant in time. So over here now, where I had cosine of theta, what can I replace cosine of theta with? 3/5, because at my instant, the cosine of theta is 3/5. Okay? And when you do 3/5 squared, and then you multiply that times 22 over 75, what do you get for d theta dt? I don't care if it's a fraction or a decimal, it doesn't matter. ahead, tell me. 0.176. How'd you got?
Wait. 105.
All right, so we're going to do 22/75 times 9/25. 0.1056.
Yeah.
Did you read it like 0, 1 instead of 1, 0? What are the units we use for angles in calculus? Radians. So it's 0.1056 radians per second. Good job. Any questions on that one? Good? All right. Then let's talk about optimization. Yes. You don't need a bulb in that projector. You can't even see the fun little bubbles on the fun little bubbles on the background. See them on there, but you can't even see them on the screen. My bulb is up. January was so long, and then February just boom. I think I just slept through February. And it's not that many days, like 3 days shorter should not make that big of a difference. No, 3 days should not make it feel like it didn't exist, but it did. All right, so your essential question says, how do you find the absolute maximum and minimum of a function? Now that part you already know how to answer, okay? And we'll review through that extreme value theorem. But what optimization is going to do is it's going to apply the extreme value theorem to actual situations where you would want to know the maximum or the minimum value of something in that situation. Okay, so the good news is that really the calculus here isn't going to be new to you, because it's the same theorem that you did last semester, and then we talked about the extreme value theorem before your last test, and so now this just means you get to have more extreme value theorem on this test, which is good because it's the third time it's been on a test, so you should really know it at this point, right? So it's just going to be an application of the extreme value theorem. So what we're going to do is we're going to be given these situations, and we're going to want to create functions and then find the maximum and minimum values of those functions to optimize the problem. Okay, so let's review what an extreme value is. So first off, we've got to talk about what the extreme value theorem says. So when we're dealing with the extreme value theorem, the good news is there's only one condition that has to be met. What's the condition that has to be met for the extreme value theorem to apply? The function has to be continuous on the closed interval. Okay, if the function is continuous on the closed interval, what has to happen on the interval? There has to be a maximum and there has to be a minimum, right? It's there's got to be a tallest person in the class, there's got to be a shortest person in the class theorem, right? Obviously, if we shut the door, we don't let anyone in and we don't let anyone out, someone has the minimum height in here and someone has the maximum height in here, yes? Okay? So the problem with the extreme value theorem is that it is an existence theorem, meaning it says, hey, there's going to be a maximum and there's going to be a minimum. All right, go find them, right? It doesn't give you any ideas on how to find the maximum or minimum on that interval. So we have to kind of combine it with Fermat's theorem to be able to talk about where these extreme values might occur. So what does Fermat's theorem say? Do you remember? Or can we look at it? Kind of. Fermat's theorem says that if what? Look it up. I want you to look. We just did this a couple weeks ago. It's not the endpoint one. It has to do with the critical numbers. If the derivative equals 0, I think you're saying it backwards, because if the derivative is 0, does there have to be a maximum or minimum? No. So if there's a maximum or a minimum, and the derivative exists at that point, what has to be true about the derivative? It must be 0, right? Okay. So Fermat's theorem basically introduces you to the idea of a critical number, which says that on the interior of the interval, meaning we're ignoring the endpoints, right? On the interior of the interval, if we want to know locations where that maximum or minimum might occur, then we're going to look for places where the derivative is 0 or places where the derivative is what? Undefined, right? Because we know that those are kind of the places that we might need to look to see if there is a maximum or minimum at those points, right? And then we talked about the converse of Fermat's theorem, which we just talked about, is not true, because that says if the derivative is 0, then there's a maximum or a minimum. And here's our go-to proof that that's not true. X cubed, right? X cubed at 0 has a derivative of 0, but it's not a maximum or a minimum because it's increasing, flat, and then increasing, right? Okay. But Fermat's theorem at least tells us inside on that interval, in the interior of that interval, if the maximums or minimums occur there, they're going to occur at what we call those critical numbers, which are going to be places where the derivative is 0 or undefined, which means your function would have either a horizontal tangent line there or a vertical tangent line there, or an abrupt change in slope or something weird going on like the absolute value function. Okay? So you just established the relationship. The relationship between critical numbers and extreme values says that if the function's going to have an extreme value, then it's going to occur at a critical number, right? If you're looking at the entire function, like think about x squared, the only place where it might have an extreme value is where the derivative equals 0 or where the derivative is undefined, okay? But when we deal with the extreme value theorem, then we're limiting ourselves to a certain interval on that function, right? Which introduces a second place where these absolute maximums and absolute minimums might occur. And where's the second place that the absolute maximums or absolute minimums might occur besides the critical numbers? The endpoints, okay? So remember that when you're talking about relative extrema, meaning just places where the function changes from increasing to decreasing or decreasing to increasing, that's all about the critical numbers, right? It's all about the critical numbers because there actually has to be a change in that slope for there to be a relative extreme value there. But if we're going to limit ourselves to a specific domain on the function, then we want to talk about the absolute extrema, then we have to start kind of thinking about the endpoints there, okay? So to find the absolute maximum or minimum of a function, you're going to compare the y values of the critical numbers with the y values of the endpoints. And we know this, okay? To do this, we find the derivative, right? We set it equal to 0, we figure out where it's undefined, then we make our little t-chart, we put our critical numbers and our endpoints in the x column, and then the y values of the original function that correspond with those in the f of x column. How do we determine which one's the maximum and which one's the minimum? Pick the biggest y value, that's your maximum, right? The smallest y value, that's your minimum. What if the biggest y value occurs twice? Like what if at x is 2, y is 7, and at x is 4, y is 7? Yeah, it's still the absolute maximum, right? 7 is the absolute maximum. It just occurs twice, right? So you would say the absolute maximum value is 7 when x equals 2 and when x equals 4, right? So that's totally possible. And, you know what I mean, if you think about, like, let's say you had a parabola, right? And you wanted the absolute maximum and minimum from here to here. Well, the minimum's going to happen here, right? But if these things are equally far away from that vertex, then aren't they going to have the same Y value? So that maximum value would occur twice. So it's the same value. It just happens more. It would be like if two people were the same height and they were both the tallest. That's allowed, right? That can happen. Okay. So what is optimization? Okay, well, optimization, like related rates, is one of the most common applications of the derivative. Okay, and optimization is probably one of the applications of the derivative that you're going to be able to see how it might actually be useful, and that there's probably people whose job is to optimize things. Okay, now they probably have like a computer, because the functions that we're going to deal with are going to be a little more simplistic, so that they're, you can find the derivative and you can find the critical numbers without it being really disgusting, right? But, if you owned a company, wouldn't you want to know how to maximize your profit? Wouldn't you want to know how to minimize your costs? If you were going to construct a bridge, wouldn't you want to know the way to do that using the minimum distance, so that you use fewer materials and it ends up then costing you less money? Right, so you can kind of see how wanting to know the maximum value of a function or the minimum value of a function is going to be something that people in life might actually want to know. Okay, so when we do these problems, if we're looking for the greatest profit, the least cost, the least amount of time, the optimum size, that's all dealing with a maximum or a minimum, right? Anytime it says we want to find the greatest area that we can enclose, well, that's the maximum value, right? If it says we want to know the least cost, that's the minimum value. So it's all application of that extreme value theorem, okay? Every time we do this, it's just using the extreme value theorem over and over and over and over and over again, okay? The difference is that I'm not just going to give you a function in an interval and say, find the absolute maximum, find the absolute minimum. I'm going to give you the scenario. We're going to have to write the function and then determine where that absolute maximum or absolute minimum occurs. Okay? Oh, I thought you were talking about your cruising in the Jeep.
Yeah, I am. My mom would pick up her car Saturday, though.
Well, that's good.
I was good to go.
It's too fancy and take this old
I was
rickety
dressed
Jeep.
up, and I was like, I don't want to drive that dressed up. And she's like, I'm blaming you. She said, I wouldn't want to look a lot.
Thanks, Mom. At least you understood.
I would break down.
If they made you take that to college.
Yeah.
All right, so the good news is that we're going to kind of, just like we did with related rates, follow a set of steps in order for us to be able to do these problems. Okay, now, once you get to step 4, then it's just extreme value theorem. Find the critical numbers, figure out what your endpoints would be, test those, decide what the maximum and the minimum are. Okay? Everything else we do before is going to help us create the function that models our problem. Okay? So it might be that we need to identify what we don't know and what we're given. Sometimes we might need to draw a picture. Now, if the problem's about maximizing profit, there's not really a picture to draw, right? But if the problem's about maximizing area, then it might help you to draw a picture. Okay? Just kind of depends on the context of the problem. Then we're going to assign variables to the quantities that we know and the quantity that we're trying to maximize or minimize. So it might be that we've got an area, we've got a length, and we've got a width, or whatever the case may be, right? Then we'll write an equation that relates those values together, and then from there it's the calculus. Find the derivative to get your critical numbers, test your critical numbers and endpoints to figure out what the optimal values are going to be. All right, I'm going to give you. This page is actually straight out of your textbook that's under your desk, but that way you don't have the textbook on your desk. And the first couple of examples that we do are going to come off here, and then I have another sheet that I'll give you, and we'll do some more examples off of. So let's just. We should be used to it.
I knew it. I knew it. I didn't know how to do it, but hope you aren't using the first. I was trying to find books. I thought you'd think. I used to go to the holes.
What?
I mean,
You're in what holes?
that's what I always do. I'll forget the whole bunch.
Forget the whole bunch of.
It's like 15.
I know. I told y'all I failed. I'm sorry. I even hole punched the pages where like your homework problems are going to come from, and those have staples in them, which means I have to hole punch them like 4 at a time, and I forgot to hole punch these. I failed. I'm sorry. All right, we're going to look at number 10. All right. In number 10, it says a box with a square base and an open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. Okay? So let's start by stating what is given to us, and then we'll draw a picture, and from there we can figure out what our unknown values are. Okay? So tell me what we know. The volume is 32,000 cubic centimeters. Okay? We're trying to find the dimensions of the box that do what? Minimize the amount of material used. So we got to think about in terms of the geometric shape what the amount of material used represents. Okay? So if you're going to make this box, right, and we're trying to minimize the amount of material used, then what you're trying to minimize is the surface area, right? Because you want to use as little amount of material as possible, so it means you want like the width and the length and the height to be as small as possible, so that you obviously save money, right? Because the less material that you use, the less money that you have to spend. Okay, so when it says to minimize the amount of material used, that's always talking about surface area. Okay, so we're trying to minimize the surface area. Okay, so we probably need to draw a picture. Tell me about our rectangular box.
It's a rectangular prism with no top.
Yeah, and the base is a square, right? Okay, so, you know, I'm not like an artist, so my drawings aren't going to be perfect, but especially because I always draw things sideways, so we're going to just go with it. It's going to look like a cube, but we'll just label things appropriately, okay? I know.
That was good.
It's okay, just do the best you can. It doesn't have to be a work of art. I know, my top is like, oh, it
I was
just,
looking down doing mine. I was like, oh, it can't be that bad.
I shook something so it got smushed. All right, so when we're doing this, we have to consider, you know, the only thing we're given is the volume, right? And when we talk about volume and we talk about surface area, we really are talking about the same dimensions that kind of help us create those values. Okay, so think about volume. What all do you have to take into consideration when you're talking about volume? Length, width, and height. Well, does our box have a length? Does it have a width? And does it have a height? Okay, so what do you know about the base of your box?
It's a square.
It's a square, which means what is true about the length and the width? They're the same, because in a square, they're the same, right? So we don't need to call this one L and this one W if they're the same. We can call them the same variable, yes? So what variable do you want to use for the length and the width? I'm going to use X. I hate using L. If I have to use L, I will, okay? So I'm going to say the length of the box is going to be X, and the width of the box is going to be X because square base, right? If you want to like make a note that it's a square base and that's where this came from, that's probably not a bad idea, okay? What other dimension do we have to consider? The height, so if you want to call that H, you can. If you want to call it Y, you can. It doesn't really matter as long as you tell me what variables you're using for what so that I can make sure when I'm grading that I can catch if you make a careless mistake somewhere, it's easier for me if I know what your variables represented.
And
Okay?
surface area.
Yeah, we're going to have to write an equation for that, right? Okay, so let's think about the surface area. I'm just going to call that A because, you know, area. Okay. Surface area is the area of all the sides of the box, right? Okay, so how many different sides and bases does our box have? 5, right? It has 4 sides and it has a bottom, right? Okay, so could we figure out the area of the bottom of our box? Yeah, what would be the area of the bottom of our box? Length times width, which in our problem would just be x squared, right? Okay, the area of the base is going to be x squared. So if you want to write that, area of base. And then we need to know the area of each side, yes? Okay, well, how would you find the area of one of these 4 sides of the box? X times h, right? Think about it, it's just a rectangle, right? So the area of this rectangle would be x times h, yes? Okay. How many of those do we have? 4 of them, right? There's 4 sides to a box. So we're going to take the area of one base, because that's all we have, x squared plus 4 times the area of the side, which is xh. Okay? Obviously, I did not want to find the derivative at this point. Agreed? Because you've got X and you've got H, and area depends on both of those things. Agreed? If you change X, will it change the area? If you change the height, will it change the area? Yes. Okay. So what have we not used yet that we have to use? The volume, right? Because the volume of our box has to be 32,000 cubic centimeters, right? Okay. So could we now also write an equation that represents the volume of this box? How do you get volume? Length times width times height, that would be what? X squared H, okay? And we know that X squared H has to equal what? 32,000, because you were given that in the problem, right? No matter how I create this box, no matter what I make X or what I make H, the volume of the box has to be 32,000, yes? Okay? So could I solve this for H? Yeah, what does H have to equal then? 32,000 over X squared, yes? Okay. Because before I can talk about the maximum or the minimum of this surface area, which is what we're trying to do, I've got to have this surface area equation with only one variable in it. I can't do anything if it has two variables in it, okay? So now in my equation, what can I replace H with? 32,000 over X squared. Can we simplify that? I hope so. What's 4 times 32,000? 128,000. And then if you have X on the top and X squared on the bottom, you really just have what? An X on the bottom. Okay? So now we have a function for our surface area in terms of the length of that base, yes? Okay? So now we can actually talk about the minimum value of this function, yes? Because it's a function written in terms of one variable. So if I want to minimize that surface area, I need to know the critical numbers, yes? To find the critical numbers, we have to find the what? Derivative. So I want to know the derivative, which we'll call a prime. What's the derivative of X squared? 2X. And we should know how to do this, yes? What happens when we take the derivative of a constant over X? Change the sign, leave the constant, and the X becomes X squared. Good job. Okay. So there's our derivative, yes? Can we figure out when that's equal to 0? We should be. How do you want to solve this? We can do this pretty easily. Move the fraction over to the other side, which is going to give us 128,000 over X squared equals 2X. Right? So if we multiply, then 2X cubed has to equal 128,000. So X cubed has to equal 64,000. So the only real value for X that you're going to get there is what? 40? Okay. All right, so when we use the extreme value theorem, that's our only critical number, but technically, what do we also have to consider? The endpoints. Now, in a lot of these problems, the endpoints are going to be obsolete. They're not really going to make mathematical sense, okay? Especially in these geometric problems, but we are going to do some where the endpoints do matter. So I want us to think through what the endpoints would be, okay? What does X represent in your problem? What do we define X as? The length and the width, right? Okay, so this is going to be a stupid thing to even think about, but could we let the length and the width be 0?
Yes.
If we do that, then what's going to happen to the surface area? it's going to be 0, right? It doesn't make any sense. But in reality, the smallest x would be 0, which would mean you wouldn't have a box at all. Is that really going to be very helpful to us? No, okay? So what I do when these endpoints don't really matter is I like figure them out because we need to show that we considered them, and I just cross it out because it doesn't make mathematical sense, okay? So then let's think about what's the biggest that we could make x. Well, the biggest that we could make x would be if we didn't use any of the material for the height, right? We put all the material in the base, yes? We just had a big old rectangular square. I don't think that's going to be very good for shipping things, yes? Okay? So you have to use this volume equation to figure out what that would mean, okay? So if I make h obsolete, like pretend there is no height, what would be the biggest value that I could use for x so that this would still be true? How would you solve this for x? Take the square root. So what's the quote-unquote biggest that x could be? The square root of 32,000, right? But then is there any material left for the height? So do I have a box at all? No, right? So, that's not really going to make any sense either. So I'm just going to put a line through it because it doesn't really matter. Okay? Now, if you look at your problem, you can figure out that if you did that, the height would be 0, so this would go away, and the area of the base would be 32,000, but you don't have a box, so that doesn't make any sense, right? It doesn't really make any sense in the context of the problem. So what did we find as our critical number? 40, okay? So I want to know what that surface area is going to be, yes? Okay, so how do we figure out what the surface area is going to be when x is 40? Yeah, so look at your surface area formula, right? It's a equals x squared plus 4xh. So I know x is 40. How could I figure out what the height would be when x is 40? Use this one, right? So when x is 40, what is h? 20? So what is that minimum surface area? 40 squared plus 4 times 40 times 20. What is it? 4,800 or 1,000? 100? Okay. So the minimum surface area is 4,800. If it's area, what kind of units are we going to have? Yeah, centimeters squared, right? So it's 4,800 square centimeters when x is 40 centimeters and h is 20 centimeters. So if you want to make a box that has a volume of 32,000 cubic centimeters, then the way you're going to do that with the least amount of material is to make the base 40 by 40 centimeters and the height 20 centimeters.
So is there technically not like a different value for the maximum and the minimum?
Well, technically, the maximum surface area would occur when all of the material was used in the base, but then you don't really have a box. So it would still make the biggest surface area. It would just be a flat rectangle, which doesn't really help us at all, if that makes sense. But it means that everything else is bigger than that, right? So all the other boxes that you could make with that volume would use more material because the surface area is larger than 4,800 square centimeters. Okay. Good? All right, let's see. Let's do... Let's do 14. All right, in 14 it says, find the point on the parabola x plus y squared equals 0 that is closest to the point 0, negative 3. Okay? So in this problem, tell me what we're trying to minimize. The distance. Good, okay? So we want to find the minimum distance from the parabola x plus y squared equals 0 to the point 0, negative 3. Okay? You probably don't need a picture in this problem. Okay? So if we want to minimize the distance, then we need an equation for distance. Now we have to think back to previous lives where we learned about the distance formula, which tells you the distance from one point on the coordinate plane to another point on the coordinate plane, like in pre-algebra.
You mean like something?
It is the square root of something, yes. Y'all not know where the distance formula comes from?
It's a Pythagorean.
It's the Pythagorean theorem, yeah.
That's I just learned how to do this. Like, I don't know what it's called.
Well, you got to. What's the distance formula? Well, think about it. If it's just the Pythagorean theorem, if this is distance, right, then this point's x1, y1, and this point's x2, y2, right?
Changing that square plus changing.
Then this distance is the distance from x1 to x2, right? So that'd be x2 minus x1, right? What's this distance? Y2 minus y1, right? So you know from the Pythagorean theorem that x2 minus x1 squared plus y2 minus y1 squared equals d squared, right? So how do you get d? Take the square root. So it's the square root of the difference in the x coordinate squared plus the difference in the y coordinate squared. Yeah? Nifty. All right, so obviously before we want to talk about a derivative and critical numbers, we got to do some work in that formula, yeah? Do we have a given point that's not going to change? What's our point that's not going to change? 0, 3. So you probably want to make this x1, y1, yeah? So we're going to replace x1 with what? 0. So if we're getting rid of the x1 and the y1, can't we just call the x2 and the y2 x and y? Yeah, okay, good. All right, so if I replace x1 with 0, what does this expression become? X squared, right? And what are we going to replace y1 with? Negative 3, so this is going to become y plus 3 squared. Okay. We still have a small problem. What is our small problem? There's still an x and a y, so we can't really do anything, okay? But what else were we given? What's true about our other point? It's on this parabola, right? Okay? So could I either solve this for x or solve this for y, and then life would be pretty easy from there? Yeah, what's the easiest thing to get by itself here? X, okay? What does x always have to equal on your other point regardless of where that other point is? Negative y squared, right? So we can substitute that into our equation, yeah? And where there's an x, I can replace it with what? Negative y squared. So if we do that, that's going to become negative y squared squared. So we probably want to simplify that sum before we try to find the derivative. What is negative y squared squared? Y to the fourth. And let's go ahead and expand out that binomial so that life's easier when we go to find the derivative. What do you get if you expand that out? y squared plus 6y plus 9. Okay. So this equation represents the distance in terms of y from the point 0, -3 to any point on that parabola, right? So this is what we're trying to minimize because we want the smallest distance that there is, okay? So to minimize the distance, what do we have to do? Take the derivative. So we're going to call the derivative p prime, okay? And in order to take the derivative, what rule are we going to have to use? The chain rule, right? Because obviously that polynomial is a function and we've taken the square root of it, yes? So what's your outer function? The square root. And again, haven't we done enough square roots where we can do this? What happens when you take the derivative of the square root? 1 over 2 times the square root, right? So in our denominator, we're going to have 2 times the original square root. Okay. And then we would multiply that times the derivative of the inside. So effectively, where does the derivative of the inside end up? In the top. So what's going to be in our numerator? 4y cubed plus 2y plus 6. Good. Can we reduce it all by a factor of 2? Yeah. So if you want to do that to make it a little bit easier, plus y plus 3 over the square root y to the 4th plus y squared plus 6 plus 7. All right, now our calculator is going to help us out a little bit here, okay? So we need to find the critical numbers, and critical numbers occur when what is true? When the derivative is 0 or undefined. So we need to know, when does 2y cubed plus y plus 3 equal 0, right? And when does what's inside this square root equal 0? So we need to put both of those in our calculator and find where they cross the x-axis. But pay attention, what variable is in your equations? So technically, even though we're looking for the x-intercepts, because your calculator graphs it in terms of x, we're really getting y coordinates, yes? I think each of them give you one value. The first one's -1. That's real. Ready?
The bottom,
They're all imaginary, which would be nice, right?
real.
So don't have to worry about that, right? Okay. In this equation, think about it, okay? We're trying to find the point on the parabola that's closest to a certain point on the coordinate plane, okay? Are there going to be endpoints? No, because what's the parabola going to keep doing? Going either up, above, or down, 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 depending on the parabola, which probably means it's getting further and further and further away from the fixed point on the coordinate plane, yes? Okay, so obviously, if we want to minimize the distance, this is going to be when it has to occur, yes? But what does the problem ask for? Find the point, right? What is this of your point? The y coordinate, right? Do we have an easy place where we might be able to figure out what the x coordinate is if the y coordinate's -1? Yeah, x always has to equal -y squared, right? So if you plug -1 into that, what do you get as the x value of your point? Yeah, -1, right? So that means that the point that minimizes the distance is going to be -1, -1. Yes. Did it ask for what the distance is? No, but could you find that? Sure you could, pretty easily. You're plugging -1 in for y, and that would give you the distance. Let's see, that would be 1 + 1 -6, which would be -4, + 9, which would be the square root of 5, I think. Would be the minimum distance. Good? All right, let's see. Let's do... I'm going to do a good area, but there's not one. All right, take one of these and let's do the first one of it. We'll just kind of jump around. I don't want to do that triangle and square.
I don't think I like these.
Why?
No, I don't know how to. They look so hard. I like related. Yeah. I think I just did that.
But you probably didn't like related rates the first day we did it either, so.
I like them better than I like them.
All right. You can either complain or you can practice and get better at it. Those are kind of your options, right? And number 1, it says a farmer has 2,400 feet of fencing. And this should sound familiar because you did this in altitude training. And he wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So let's draw a picture. What do we have that's not going to be? A river. So the squiggly line is going to represent our river. Okay? And what are we going to do? Build a fence that looks like a what? A rectangle. But we don't need to put any fence on the river, so our picture is going to look like this. Yes? All right, so what are we given? He has what? 2,400 feet of fencing. Which in terms of the geometry in the picture would mean what is going to be 2,400? The perimeter. Okay. So let's write an equation for what we know, and then we'll write an equation for what we're trying to optimize. So we probably need to give these some values. We have this length here. What do you want to call that? I'm going to use X and Y. You use whatever you want if you want to make life more complicated. All right, so can we write an equation for our given information, which is the perimeter? How do you find perimeter? You add up all the sides. So what's that going to be?
2x. 2 plus
X plus 2y has to be 2,400, right? Because obviously to maximize the area, he's going to want to use all the fencing. Okay. And we're trying to find what? The maximum area. Well, how do you find the area of that rectangle? X times y. Okay. So if we want to maximize that, then we probably need to write it in terms of one variable. Yes. So what can we use to establish the relationship between X and Y? Yeah, the perimeter equation. And what's the easiest way to manipulate this? X equals 2,400 minus 2y. So now in the function that we're trying to maximize, which is our area function, where there is an x, we can replace it with what? 2,400 minus 2y. Okay. All right, let's distribute that y in. So our area function is going to be 2,400y minus 2y squared. And really, you don't even need calculus to do this because that's a what? A parabola that's upside down, so where's the maximum going to have to be? At the vertex, right? So you did this exact problem in altitude trig. It's just now we can do it using calculus instead of having to remember formulas. So if we wanted to find the derivative of this to find the critical numbers, what is the derivative of your area function? 2400 minus 4y, yes? So our critical number is going to happen when 2400 minus 4y equals 0. Which is going to happen when y is what? 600 something? Is it feet? Right? Okay. All right, so if we think about our extreme value theorem, our only critical number is that y is 600 feet. Okay. He could use all the fencing on the sides, yeah, and not any on this side, right? But then is he actually enclosing any area? No, right? So if he uses all the fence for x, then there's no fence left for y. That would be your minimum. Your maximum would be that he would use all the fence on the sides, right? Okay. How much fence does he have? 2,400, which would mean each side would be what? 1,200. But then is he enclosing any area? No. So obviously those are not going to maximize the area. Agreed? Okay. So how are we going to find the maximum area? Plug 600 into this area function. What's that maximum area? 720,000, like this, square feet. Okay. So the maximum area is 720,000 square feet when y is 600 feet. And how can we figure out what x would be? There's a couple ways. You know the area, right? How do you get area? Length times width, right? So couldn't you take the 720,000 and divide it by 600 and that would tell you what the width would have to be? Or you could go up to that perimeter function. Either way. Somebody tell me what x has to be. I think it's 1,200. Yes. Good. So you really can do that problem without the use of calculus, right? Because the function that represents the area ends up being quadratic, right? But if it's not quadratic, then you have to have calculus to find the maximum and minimum, because otherwise you just have to graph it and then change your window 4,572 times until you actually find the maximum, and then find it on the calculator, and then hope you typed it all in the calculator right, all those kind of things. Okay. Any questions on any of those three that we were? Emily, which one? Huh? You didn't type it in right.
I'm just figuring out where the 600.
Whatever you're trying to maximize, that's what you find the critical number for. Okay? The other equation is just to help you write that in terms of one variable. So we can't find the critical numbers until it's adjusted one variable. Okay? So like the given information, like in the first problem, the volume, and the second problem, the point, and then the third, or the parabola, and in the third problem, the perimeter, that's all given to you just to help you write that equation in terms of one variables. Okay? Yes? You would have to do it in terms of those variables. Like your answer would be in terms of the radius and the probably something about the equal. But we won't.
I like the picture.
right, we're gonna do some more of these tomorrow, but I'm gonna give you the worksheet that your homework comes off of, so that you can start practicing on some of them tonight. So take one of these and pass it back. The first part, the 11 through the 41, comes from like the first part of the worksheet, and then the back is exactly what I already gave you, but I gave it to you again, so it's all connected. And so the bottom two come off the back. Okay, does that make sense? And this is hole punch. I think I was so stressed about hole punching on with staples that I forgot hole punch.
At least you do.
So if you want to get a circle on this, which one you're touching, that's probably the best. It'd probably be a good idea, like just a circle on the worksheet if you want to, which one to do, if it's confusing to you. If it's a half sheet, then you have to hole punch it where it gets two holes. Because if you only give it one, then it's like,
I like a quarter of a sheet, and it was
then
only
it can't have two holes. So you have to do it the other way.
you didn't hold it.
I know if I don't hole punch it, you're going to use it. If I hole punch it, then you really have to not do it.
And he'd be like, all right, pull this paper out from 2 months ago. And I'm like, you get us 18 papers a day.
Shoved in a folder or something. So many fish.
Not that happy when they teach it.
This Moscow is pregnant for she
Yeah. She's like, so how are you?
Hi.
What? So how was your weekend?
Or get talked about, she's like, no, like,
There's like she wasn't kidding.
Every time they call it,
The first is on the first 3 pages. The last two are on the back. Don't look at
they're
the top.
probably like, I called a fan of like, okay, that's and one time I caught an audit, got it, never knew the girl she was, so I thought girls was like, never caught it.
Yeah, Kylie got her 2000 after each year because like I called her and I knew this girl for
This.
out of your class. And she's like, yeah.
Y'all have a good day.
I just had burlesque show and I was like, it helped me.